So I work in the data science and open source software and the Python world and all that stuff. So if you like Python, love data science, you probably have touched something that we use or know of what we do. If you don't like any of those things, then you probably either don't know who I am or don't like anything we do. But I come to sort of decentralized computing, de-webcamped kinds of things because for a long time I've had a personal interest in that whole technology space, this whole technology space. And so here I'm going to talk a little bit about Python bits, but not too much. This is really talking about WebAssembly. And what's interesting is that I think there's an intersection between sort of my day job in the Python data science AI space and my long time personal interest in decentralized computing and peer-to-peer technologies. And I think they intersect in a very interesting way with WebAssembly. So I'm going to talk to you a little bit about that today. And the title of my talk is Our Portal to Portable Computing, which is a little hard to say, especially if you have a little bit of wine. But before we sort of investigate the question of portable computing, we can start by asking the question, what makes software not portable? Well, and what makes it not portable is that when we write software, we're sitting on top of a stack of other things, right, in the most idealized way. So this is true now, of course, from a Python perspective, we have an explicit language runtime, it's an interpreter, but people working in compiled languages recognize that, of course, there are core language bits from the compiler that also get loaded in as a runtime. So when you see runtime there, it doesn't just mean interpreter, and it's certainly not just an interpreted language ecosystems problem. This is really true for everyone. And this, hopefully this is not too controversial of a stack. And what I would say is that what makes software not portable is that every single one of these blocks is a leaky abstraction. And by leaky, it means that if you're programming at that level, you're going to stumble over holes in it. But it also means that you can poke through that hole and touch something underneath you're not supposed to touch and make software that then becomes very unportable. And then between each layer, there's something else that's a little subtle, but if you think about it, it's true. Between every layer of abstraction, there's usually this install or compile or configure step to kind of mate these things together. So it's not like a stack of Legos that just have like, sub-millimeter precision that just snap together. You always gotta jam them together a little bit with a YAML file or an INI file or a Docker file or something, right? Something kind of like smacks these together. Make file, configure, autoconf thing. And this configure step usually it usually includes a lot of opinionated sort of configurations about the layers below. So it's not, again, the bottom layers that show up, they don't just give you perfectly spaced studs that are in the right spaces all the time. You can choose to have the studs show up in a different place or have 10,000 new studs over here in a different directory. And so that set of configuration options is, again, one of those things that happens. And so by the time that we take these Lego pieces together, what we've actually done is glued them all together into the like horrible melted blob of plastic. And that's why it's not portable. And so the question, I think, if you start from go back to the very beginning, you say, what's the point of all of this? Why do we do all this stuff? And I would say the reason we have software at all is because we want people to harness the power of computers. We want to let them express their ideas at a level that they're interested in without being encumbered by any unnecessary complexity. Like in an ideal world, if you could wave a magic wand, this is what you would just give to everyone. So a school child wanting to make some art thing can do it. A teenager wanting to make their own custom game can do it. A scientific software developer who wants to harness a supercomputer and just write exactly like the 10 lines of math that they want to write, they can do it, right? In an ideal world, that's the software ecosystems that we'd have. That is not the software ecosystem we have, but that's ultimately the point of it. Like, why do we code? It's because of this. This is why we don't all just write low-level machine code for precisely the chip that happens to be in our laptop this year. And so our approach to this, our fundamental approach to solving this problem, has been the same approach since about the 60s, which is that we create these abstract concepts above the hardware. Right? The hardware only has binary. The hardware doesn't even have floats or ints. It kind of does, but you can kind of like, people jerry-rig that stuff. It's just got bits. And so anything we put above those bits, those are these attempts to build this ladder of abstraction, and it works reasonably well. And it's an interesting footnote actually. I put that here parenthetically. There's an actual time when the computer science, field, they didn't know if compilers were possible. right? So there was this language called Algol that was developed, and these people were trying to figure out, can we make an Algol compiler? And someone, some people thought no, others were like, well, it'll take a long time. Then they hired the summer intern in, and he like built it in the summer. And the intern's name was Don Knuth. So they were like, wow, this is a really bright kid. But now we know we can make compilers, right? So this is not something, and this is in the 60s. So we've sort of pulled the same hat trick over and over and over again, making compilers. And so since then, the 70s, we just live in this long shadow of the 70s. So much of what we use is still dated from that era. And of course, I have the 80s in here as well, and the 90s. But just to give you a sense of, we still use Ethernet. We still use Unix. Many of us have to support users on DOS. Even though we call it Windows now, there's a whole lot of DOS in there. So, and every single one of you gets paid out somehow through VisiCalc, although we call it Excel now, right? So there's a lot of the groundwork of how we think about computing and the act of software construction that's been anchored in the 70s. And I would say that we've certainly moved beyond. We've moved into a post-PC era now. I think that's not really a controversial statement. But all of these blurred lines that happen is because we've had this continuous economic revolution. Let me say that again. Continuous economic revolution from the PC, and the PCs kept improving, and then consumer broadband came in. And that kind of kept getting better, speeds got faster, and then Web 2.0 came in with interactive client-server computing. And while that was going, part of that mutated into social platforms. And while that was going, we got portable supercomputers in our pockets, right? And then like it just keeps going. Cloud, AI, all these things keep happening. And the really interesting thing about all this stuff is that at no point do we stop and say, oh, well, you know what, this is really, we have rickety ladders stacked on rickety ladders stacked on rickety ladders. We should stop and maybe build a really good concrete stairwell and then build from there, maybe. But no, we do not. We just keep slapping stuff on top. And because it hasn't led to the collapse of civilization just yet, we believe this is an okay thing to continue doing. But the important thing to say is that this is all frozen accident, right? This is all frozen accident. And there's this great quote I love, which is that science makes progress because scientists stand on each other's shoulders. Computer scientists progress by standing on each other's toes. And this is okay because they get paid handsomely for it, and it's still better than not having working software. But all of us, I think, in this room as technologists, we've played with this stuff enough, we've looked at this stuff enough to understand that there is no spoon. Operating systems are a myth. Programming languages are a myth. Floating point is a myth, right? The most cutting-edge AI today, they're using what? 16 and 8-bit integer math. They use fixed point, not integer, sorry, fixed point math to make things go fast inside those CUDA cores. So every single thing you thought you knew about what any of this stuff was or why we needed it, it's basically, you can decide today to stop believing in all of it. All right, I give you that freedom. I sometimes choose to exercise that freedom. And the reason it's important to exercise this freedom is because we're now in a really interesting time when we can rethink this. If we start backing into that question of why do we do computing? Why do we write software instead of soldering things together to make cool blinking lights? And the reason is because there's all these different things people want to do. Some people want to make games. Some people want to make interactive art. Some people want to do spreadsheets, all sorts of stuff. So if we start from there and then we figure out, going backwards, what is the minimum set of abstractions we need between the hardware and the application in order to, actually have this work? Then it's a very different question, right? It's then sort of saying, let's say we find ourselves in this part of space. Let's burn down all the ladders. Control Z, remove all the ladders. How much? What do we actually need to do to go from ground plane to where we're at for this application? And this picture on the side is something that's from a talk I gave in 2013 when I talk about that when I was giving a talk at a PyData conference in New York. And I had this thesis that we could build dynamic compilers and just-in-time compilation that would take Python and take it at different levels of abstraction down. And we succeeded in doing that. And we have a project called Numba, which is a dynamic just-in-time compiler. It can target GPUs, it can target CPUs, but it actually takes your Python code that a data science novice 2 weeks out of a boot camp could write, and it takes that code and it can make it into machine code faster than if you hand-tuned some C++, right? And the reason we can do that is because there's all sorts of things that the computer knows how to do. Once it actually has the actual code and the actual values coming through and the actual types, it can do all sorts of great stuff for us. And so the reason for thinking about it from this perspective is because my assertion is that this technology, WebAssembly, that's just recently become a standard in the last couple of years, WebAssembly completely changes the game. Literally, it changes the game. It flips the script on 40 years of software infrastructure, 40 years of frozen accent, 40 years of PC Wintel duopoly. WebAssembly changed. Wait, this is being recorded, right? Okay, that's fine. I got friends at Microsoft and Intel. They know what I mean. But the idea here is that WebAssembly, what it actually is, the way it came about was that people had a pile of JavaScript on the web for all sorts of maybe useful things and sometimes maybe kind of creepy, crappy things. But whatever, there's a pile of JavaScript on the web, and people kept realizing this JavaScript, we have to optimize it, we have to optimize it, we have to optimize it, and the JavaScript runtimes in the browsers got better and better and better at optimizing, and the way they got better was because they would take the JavaScript and build shadow classes, they would do lowering, they would do all sorts of stuff, amazing, amazing, like theoretical CS compiler stuff they would do. And then people started realizing, wait, if I write my JavaScript in a particular way, I can then hint to the optimizing just-in-time compiler that this is really, really, really an int. Really just treat this like an int. And if I do this thing over here, I'm telling it it's this other kind of value. And if I do the other things, it's telling the low-level thing, the low-level JavaScript interpreter, I'm signaling something else to it. And so eventually there was this little project called asm.js that came about, which was all sorts of goofy, like, syntactic hacks to directly convey to the underlying runtime what you mean in JavaScript. So it's really very interesting and very odd project. But that then evolved into this thing called WebAssembly, which is that now the web interpreter, or the JavaScript interpreter that powers all the browsers, those JavaScript interpreters, they have a front end which actually understands JavaScript, the language, and it converts that into low-level instructions for a virtual CPU. And that virtual CPU is the WebAssembly runtime. But that virtual CPU instruction set is reified. You can target it with a tool chain. You can just, it is a 32-bit CPU, it's a 64-bit CPU with 32-bit memory space. And what's really interesting is this compiler tool chain built on LVM called mscripted has come around that can compile most C or C++ to target this WebAssembly. So that's super interesting, right? You don't have to write JavaScript anymore to target the web. And the other thing about this is, even though it sounds like a super cutting-edge, goofy thing, it actually runs everywhere. It runs on mobile Safari, it runs on Android, it runs on every major desktop browser, it runs on the Opera Mobile. 4 billion installed devices worldwide have this completely portable, highly optimized, highly secure runtime available. Because keep in mind, the security of this thing, it is what powers Gmail, Amazon.com, everything that you access through the web runs inside the same enclave. So this is really the CPU at the heart of every single browser tab you have. So this is what's really cool. You can use tools like mscripton to provide a pseudo-POSIX environment and take any of your legacy code, well, not any of it, but a lot of it, and compile that to target this virtual CPU in the browser. This means you can run C code in the browser. So there's projects like DOSBox, which do our DOS emulation. They compile the whole thing to WebAssembly. It loads in a web page. You load in, then you hook up a virtual file system to it, and now you're running Doom and SimCity and everything. In all the games that I grew up with that I loved, I can run them in the browser. Not because people recoded them in JavaScript, but because people compiled them. Actually, people didn't compile them. People compiled DOS, a DOS emulator, to target this virtual CPU, and then they just load in those game binaries and exes unmodified. It's kind of a trip. So the other thing is, for servers, this is the game changer. And if you go to things like KubeCon and you look at the amount of interest in WebAssembly, it's because this is actually the thing that's much better than Docker for a lot of purposes. Is much better because this is an isolation. This is isolation truly at a below the OS level. But anyway, it spins up super fast as well because browser tabs have to be fast. So the key thing here, that's the really, really big takeaway, is that with this technology, every single person that can run a web browser tab, which is a lot of people on the planet, they actually have a uniform runtime that's congruent with every other person that has a browser tab. Until this point, we did not have that. Because you would have a Windows box, and I've got a Linux box, and they've got a Mac, and someone else on a Chromebook, and someone else on an old Android tablet, and none of these, you can't ship a single payload to all of these people and have it work until now. So earlier in the year, I created a thing called PyScript, and PyScript takes advantage of this. It takes advantage of the fact that you can compile the standard C Python runtime interpreter, and a lot of the data modules that power PyData and SciPy and things like this, you can compile all of that to target this WebAssembly CPU, and now you can run these in the browser. And so there's a project called Pyodide that did this for a couple of years, really, really cool, awesome project. And then we sort of wrapped it with some framework so that you can interleave Python in HTML. I think someone joked once at one point, they're like, oh, I guess you looked at PHP and thought it was awesome, so you made Python like PHP. I'm like, you know what? Whatever works, right? But what's really cool about this is that you just have HTML. So the universal EXE now is HTML. And this is what this code, I don't know if you guys can read it from back there, but you just put a bracket py-script tag. It's a web component. And now you can just write Python code. And so the WeatherXM demo, right? That you wouldn't need a container. Right? I think that was Python because I saw a matplotlib graph. But you should be able to run that whole thing with just an HTML file with PyScript. And so it's a layer and a stack of things. And what's really interesting is that the Python can call the JavaScript, and the JavaScript can call the Python, and the JavaScript can touch and frob the heap of the Python process because it's just one big old JavaScript array. Your entire memory in WebAssembly is a JavaScript array. It's really amazing. So now every single person, not only does every single person in the world with a web browser tab have a uniform computing environment, they can truly be peers to each other because you can use things like WebRTC and you have access to WebSockets, things like this. So you don't have to get them to install Docker. You don't have to like port your code to run on whatever Alpine Linux is in the Docker. You literally just can run the stuff you know how to run. And there's Rust that's compiled to WebAssembly. There's all sorts of stuff that compiles to WebAssembly, not just Python. Although the Python side of the world is what I'm sort of really trying to push forward on WebAssembly. And it's not just cheesy little hello world things. This is full on. So for instance, these are some of the demos we have at PyScript.net. The one in the very front, that is the New York taxi cab data set, a very large data set loaded into an interactive Pandas and DeckGL 3D analytical environment. In the back, that's Python, PyScript talking to WebGL, doing, again, interactive 3D sort of stuff. On the left, you can't really see, it's a little obscured, but it's actually an interactive machine learning example with scikit-learn. Again, all running client side. All of these are single HTML files that I can give to somebody on a USB stick, somebody anywhere in the world, they can load it up and it runs. And this is really the amazing thing. I will quickly go through why Python matters and why I'm interested in the Python side of this, and I'll loop this back around to why maybe you guys already see where I'm going with this on the WebAssembly thing. But the reason why I'm so interested in Python, this ties back to that thing about why do we do software at all. It's to empower people to do whatever it is they want to do with computers. If you guys ever go back and look at old, like 1970s magazine advertisements or newspaper advertisements for computers, the idea was that you would write the code to do the thing you wanted to do. So you would buy an Apple II or something, set it up in the kitchen, and you'd punch in like a recipe software for like in BASIC, and you'd have your recipe cookbook thing on your computer. And this is like a reasonable thing that people expected others would do. And so this idea that computers are tools of creation, not merely swipe left, swipe right, get mad, get thirsty. This idea that computers are tools for creation and that they're bicycles for the mind and all this stuff, that actually is part of what motivates our mission here, at Anaconda, which is to empower lots and lots of people to do data analysis, lots and lots of people to be data literate. So Python as a language has proven to be easy to learn, designed for readability. People can sort of casually take it up and then program by example. But something for this crowd to be aware of is that Python is not like a lot of the other scripting languages, and that one of the really cool things about the Python runtime, the interpreter CPython, is that it has a very consistent and simple low-level ABI at the C level, at the C code level. So you can build extensions kind of beneath the waterline and tag in, like couple into this like iceberg set of features underneath the Python interpreter and extend it to do deeply performant, really large-scale computation for math. And so that's why Python has taken over for data, for numerics and things like that. This is the thing. And the reason I bring this up to whoever I can is because I realized after reading Hacker News for many years now that no one really understands this. And so I have to keep telling everyone this. It's not the same as Ruby. Python is not just a less efficient Perl or whatever. Python is very unique in that its runtime is extremely extensible, and it showed up at the right time that a bunch of scientific computing engineering nerds took it and extended it with all these semantics for doing large-scale vector and tensor math. And so it is a Honda Civic with these mounting bolts for the warp drive, and that's why people use it for AI and for all sorts of large-scale computation today. But where that leads us to, since I brought up AI, where the world is going is back to the future in the sense of we originally created computers to do prediction. That's what they were about. Whether it was predicting, where the gun of a battleship should point, or whether it was predicting the entire economy of was it Chile or Peru, whatever the Cybersyn thing was. The point is we use computers to do prediction because that was the single most important thing. Tallying things, counting things, basic statistics, that was not the most important thing at this time. And then, adding all sorts of fun computer, consumer entertainment kinds of things, that was completely ancillary. We're back now to a time where everyone cares about prediction again. Prediction in the large for entire economies, prediction in the small for robots trying to navigate a factory floor. So the entire world we're steaming into, just running into full speed, is a world of connected sensors, actuators, computing-rich environments everywhere at the edge, everything running predictive loops. And so with all of that being out there, everything shedding data exhaust, everything making predictions, we really have to empower the world's population with data literacy. It's not just good enough for a few people to know how to build this stuff and everyone else just uses it and just chills. It's really, really important that we see data literacy, not software development, but data literacy as a fundamental human skill, just like being able to type on a computer, just like being able to read a book, or being able to be basically mathematically literate. If we don't solve this problem, if we as a species do not intentionally tackle this problem to solve it, we will end up in a horrifically terrible state of affairs. It will not end well for any of us. We will do well, our grandchildren will get guillotined, right? So that's what we have to avoid. And so to give you a really concrete picture of this, there's many measures and analyses of how many programmers there are in the world. Some people say 20, some say 40 million. I like to take the number about 25 million, I think, is about reasonable. Coders. Not people who can write a little bit of code, real coders, 25 million. Well, there's 8 billion people in the world. So if you do the math, it's less than 0.5%. And out of those 25 million coders in the world, there's a lot of them that don't know math or stats, or they can't do statistics, they can't do basic data science. So we're talking about 0.1%, 0.15% of the population able to understand all of these things that affect everyone's lives. And that is not a good state of affairs, full stop. So coming back around to WebAssembly, we have this universal virtual machine that everyone has. You don't have to, you can get started by going to a web page, and you've got it. You've got all the runtime you need to play with stuff, to hack with something, to take it and remix it. And the reason I think WebAssembly succeeds as a universal VM is because it didn't start the way that all the other universal VM projects started, like the JVM or the Microsoft CLR, DLR stuff with .NET. All those started with trying to build the grand abstraction that will run all the languages. But every time they try to do that, there are many other things that are more vertically integrated and specialized tool stacks that would outcompete them. But WebAssembly instead comes around, and it sort of fell in our laps because it started with this huge install footprint of basically everyone who uses the web, and then it builds in and it sort of distilled out what is the minimum reproducible portable runtime that's good enough to run everyone's JavaScript fast enough, right? So the dream, and the reason I'm here at Compute Over Data, is because everyone has these machines that can run this portable runtime. Everyone can be a peer. And we have a language and a language environment, language tooling now with PyScript that makes it so everyone has a zero install ability to start writing code that runs on data locally, or that can easily move with a button click into the cloud. So no, you don't need Docker. You don't need to install, ironically, I'm the Anaconda guy, but you don't even have to install Anaconda. You literally just write bracket PyScript, and you're rocking and rolling. So this is ultimately the dream, is that taking advantage of WebAssembly, taking advantage of this super portable new concept of this, this new runtime, we can create really, we can kind of accelerate past the 40 years of ossified, frozen accident, and really try to intentionally build out better architectures to compute, local, edge, offline first kind of capabilities, and then putting in the hands of, again, the important thing here, putting in the hands of everyone. So it's not just a few people who know how to have the access permissions to touch a big data center and things like that. So with that, thank you very much, and I think we might have some time for some questions.
Excuse me, I just had a sandwich. So I'm loving what you're saying about the getting people involved in the system so they get to learn it. I wonder what your thoughts are on getting them, whether it's more valuable to have them be literate or have them be actual builders in the system. So in science, we have the concept of science literacy, but with distributed computing, everyone can become a participant in the system and actually contribute to building these things that affect your life everywhere.
Yeah, I think the best stakeholding is participatory stakeholding,
Yes.
right? So, so definitely, in fact, I would say that if literacy is simply interpreted in a very surface kind of way in terms of like you can read the thing and maybe grok it or convince yourself you can grok it, then you don't know when your read is too shallow, right? Until you go and try to build it and use it and put it in practice, then it could just be that you end up really in a very shallow part of the water and you don't really have deep understanding at all. And for some things, maybe that's okay. But I think for a great deal of things, it really matters a lot that people do get their hands dirty on some of this.
Yeah, at least for more than 0.5%.
More than 0.5%, right, right. There will be a gradient, for sure, of expertise.
Hi, thanks for the talk. It was really fascinating. One, I guess, kind of low-level question I have is you'd mentioned one of the beauties of Python being able to plug into C++, Fortran, libraries, whatever. I'm just curious to know if in WASM, if that's still the case or if it's only pure Python at this point.
No, that's the point, is that is the whole thing, man. It is the whole thing. So we have Matplotlib, we have SciPy, scikit-learn. There are some libraries that have built sort of native JavaScript things. So there's like TensorFlow.js and some of these things, and we can of course talk to those, right? Kind of at the high level JS FFI, but for the low level stuff, absolutely, yeah. In fact, the thing that we're struggling with right now is that there's not really a good modern Fortran compiler that can target WebAssembly. So in order to get some of SciPy working, Pyodide had to do a Fortran to C translation and then compile the C with the M-script and toolchain. But absolutely, that's the real beauty of this stuff, is that you can get that C code in there.
Thanks.
So two quick questions. One, if you ask the average very productive data scientist today how much they know about Python innards, right, the GIL or whatever the hell, probably pretty low, and they're very, very productive. What percent of people ever even know that WASM exists? That's kind of like even at the limit where we are very happy and everyone's using it. And two, you have a bunch of really smart people in this room. If you could wave a magic wand and in 1 month, 6 months, a year, had something that existed in the world, anything, tool chains, bindings, I don't know, you name it, what would you like to see?
Wow, okay, so the first question, if I understand it correctly, is most people don't understand the innards. How many of them need to know that this is WebAssembly? Is that the question?
To some degree, how many need to know that WebAssembly even exists, or the innards of
No, none of them, because none of them know what x86 mean, and they use it all the time, right? It would be interesting to do a little Twitter poll and ask people, like, does the new Apple M2 chip, which instruction set which ISA does it use? I won't even say instruction set, right? Select the ISA of that new Apple M2 chip, right? And so, no, people don't need to know that's WebAssembly. All they will know is that it is awesome, because they just go to a web page, and every data set they get has a corresponding HTML file. They double-click the HTML file, and now instead of spending hours wrangling with the CSV, reading some text file that describes the columns and trying to figure out what pandas command they need to use to like munge something, they double-click the HTML file, and up comes a rich analytical environment that has all of the views baked in, that has all of the interactive transformations they want, right? So DuckDB, right? Take your SQL database, move it anywhere, and query over data, right? Thematically very related to this conference. That's right there. And so this idea of get the user what they need at the point of use and pull this in dynamically. So that's really the theme here. And so no, all they know is just all of a sudden a lot of pain went away. There's a ton of people, of course. Everyone here is, I would assume, familiar with Docker and quite comfortable with it, or maybe not everyone, but a lot of people are. But if you look at the data scientists, it's something they struggle with, because it's not just Docker, it's all the other stuff, right? You all know what I mean. And when something fails, figure out what went wrong, like that's all very complicated for people, and all of that goes away because you're literally just going to email HTML files back and forth and you'll be fine. So that's the question number one. Question number two, waving a magic wand, what would I wish could happen? I would, for this room, for this crowd, I think what would be really amazing is if people started thinking about, well, I'll just go out on a ledge. I'll say this, right? I've been a big supporter of decentralized computing for a very long time, but I've not been a big supporter of like crypto hype, all right? And I think I've found many people in the decentralized web community who are of a similar flavor, that we see what blockchains could be good for, we see what they're totally not good for, and we see what crypto hype is, and yet there's this thing here that we need to just build really, diligently build good, credible technology. There's something very, very good there to be built. And so what I'm trying to, the reason I'm here, right, and tomorrow as well, I'd love to have conversations with folks, really think about, okay, no kidding, I think this stuff is ready now, where we can put computing alongside the data. We can put this in people's hands, we put this in people's weather stations, which looks awesome, right? I'm gonna have to get one of those things, because Austin gets lots of interesting weather. But like, this is the thing that, can we build some really, really cool use cases to get people into citizen data, citizen science, into really putting this stuff back in their own hands. I have a 12-year-old son, well, an 8-year-old daughter, but my son is at the point where he's programming and playing around with this stuff, and watching him try to do things and seeing the place that he gets stuck is really, really interesting, because he comes at it from the perspective of, I remember when I was 12, first learning programming. A lot of things were, hard, I had to learn them, but the encumbrances that he has to go through today are just stupid, right? There's like no reason for them. And so that's what I'm really hoping in 6 months' time, to make it very concrete. I would love for us to have some use cases that people are saying, oh, I got this thing, I stood this thing up, and it's effortless, and I don't have to learn all of cloud to do something very simple that I can share with a colleague.
Thank you. On this mission with you. So once we've got our tabs and the peers and the little example you just gave, how do we coordinate each other? How do we find the other peers? Have you done any thinking or a vision how that might evolve?
A little bit. Well, a little bit. I think if we produce the right kind of infrastructure, then a number of different kind of registries could emerge. Okay, so here it is. So the idea here is, I would love for us to emerge some concept, produce some concept that is not just pure data and not just code in a GitHub repo, but it's actually some combination of the two. So it's like almost like a live data set endpoint. And then anyone else wanting to compute on that has code and data lineage and provenance. And so you would put the registries of these things then, this is actually then the Merkle DAG or the blockchain or whatever you want to call it, right? And we're so close, we're almost there. There's no reason we can't just build something like that. And so that's why I'm trying to push people here kind of in that direction a little bit. But I think the registry is the data index, is the global data catalog, and it should just be a URI, right? And the key thing is compute over data. It's compute and data. It's fusing these together, so you never lose track of what data set yielded some result. And when you look at a derived data, you never lose track of what code ran to produce this from its sources, right? And today, that's almost impossible. And I did consulting at a big bank 15 years ago, and they were building an internal system to do this kind of data provenance, data tracking. It was a huge, amazing system. If you guys Google for this bank Python thing, there's a blog post about this written up that was Hacker News years ago. It was an amazing system where the data was live, and there was full provenance of every data change. Like, the data catalog was the database, was the distributed key value store, was the CVS code repo. Like, it was all one giant thing. So I would love for us to build a global, externally decentralized version of that with these components that I'm talking about here. And that, oh, no, one more.
Thanks. So you said at the start that WASM is almost like an opportunity to rethink the stack, which is really great, and I agree that it's all gone a bit wrong. When I see people doing stuff with WASM, particularly on the server side, what they seem to be doing is starting with this vanilla substrate and then slapping POSIX on it.
Right.
And POSIX has got lots of assumptions about computers maybe being mainframes and having file systems and all that sort of stuff.
Yep.
And I'm worried that we're missing a trick by just slapping POSIX on top, and actually we could come up with something better. Do you think I should be worried, or do you think that's fine?
If you have a vision for something better, you should always be worried that crappy stuff will come along and take all the oxygen out of the room, right? So in general, yes. But in this particular case, I will be pushing very hard from the data side, and many data practitioners as well will be pushing very hard from the data side to keep it at that level and not just do the WASM is just like a different kernel for your same old crap of like overburden of like POSIX stuff. And so to give you a concrete example of this, when we look at what data scientists want to do today, their data is in all sorts of different places. There will be cloud buckets. There will be CSV files locally. There will be maybe an API endpoint they want to read out of an Airtable or a Google Sheet somewhere, right? There's going to be a big table or some like database they have to query. Their data sources are in all these different places. What they don't want to do, the last thing they want to do, is to ETL all this data out of there into some giant local hard drive somewhere and then run a bunch of stuff on it. What they would really love to do is express their ideas across these different data sets in a nice way. And so at Anaconda, one of the open source projects we created, there's sort of two that go hand in hand. One is called Intake and the other is called FSSpec. FSSpec is now baked into Pandas itself as the way to reference data sources, whether it's S3 here, whether it's something else over there. So the idea is to give data scientists an expression layer where they can express the what they want to do, not the how. And as long as you keep the users at the what level, then we have the opportunity to go and synthesize the appropriate how, given the computing context, given the overall scope of the problem. And that includes scheduling certain parts of the compute graph, in data local ways, all these kinds of things. And so that I would say would be a countering movement towards that. Now, at the same time, both of these can happen. All of the server side WebAssembly folks and WebAssembly in the edge and CDN kind of stuff, those guys are going to keep doing what they have to do because they have a lot of workloads that will come in expecting POSIX. So that's going to be what it is. But yes, you're right. If that becomes if that's all it ever is, then we've lost a moment. We lost an opportunity. Yeah.
Hi. Yeah, awesome talk, and thank you for coming. And thank you also for PyScript, because we built support into Bacalhau for running Python with Pyodide, and I'm grateful that PyScript has got a lot of library authors to make their stuff work with Pyodide. So
right.
That's awesome. Thank you. I have I guess it's kind of like a low-level question. Pyodide targets Emscripten, as I understand it.
Right.
Which meant that for our Pyodide support in Bacalhau, we had to run a Node.js container. Do you see Pyodide supporting WASI in the future, or?
That is a topic. Yeah, WASI is a topic of active conversation. We are actively now. We've been supporting the Pyodide project, like funding some of the work, and then moving forward, we'll continue doing that. And that is one of those things that we're trying to help. So PyScript, from a certain perspective, it added very little on top of Pyodide, but from a certain other perspective, it added just enough to open up many people's eyes to the possibility, right, and get a lot of interest. And sometimes that's a good thing, right? That's actually a very critical thing.
Yeah.
And where we're going now is there are multiple runtimes. So there's a blog post that'll be coming out in about 4 days. Okay. So I'll preview for all of you some announcement we'll be making. But one of the things we've added in PyScript is the ability to support different kinds of runtimes. One of the runtimes is Pyodide. Another runtime is the official CPython WebAssembly build, right? Another runtime is Emscripten Forge, which is like Conda Forge, but with Emscripten and with all these packages. So it's not the way that Pyodide has a monolithic sort of distribution, and Emscripten Forge is more of a piecemeal one. And then we're also adding MicroPython, which is about, I think, 1/100th the size of Pyodide. So now you have no reason to write JavaScript again if you can write Python.
Nice.
So it will be, these are some game-changing things we'll be announcing in a week. But all of these then, to actually answer your question, is that they will force us to think about, okay, what does the file system API look like? What does the worker and web worker dispatch look like? What is a socket level API that we want to provide, all these runtimes, right? So that's going to motivate a lot of that kind of discussion.
Awesome.
Yeah.
Thank you.
And we're at happy hour time, so if, yeah, we're good? Okay, great. Thanks, everyone.